Hello, everyone. We're going to pick up with today's lecture on Section 10, Chapter 3, Section 10. So we'll call this Lecture 3, Part 10, and it corresponds to Chapter 3, Section 10 of your textbook. And the topic for today will regard linear approximations and differentials. So linear approximations and differentials. All right, so we'll start off with linear approximations first. And it turns out that if you have a function, as shown in this diagram, some hypothetical function, I'll accentuate in blue here. We don't know what it is, but it could be some sort of complicated function that could be a rational function with trigonometric components and exponential components and whatnot. But with this function, we'll assume, if we assume that it's differentiable, say at x equals a, right here. Okay, and so the point a, f of a, this is on the graph, and then if it's differentiable at x equals a, then of course we can find the equation of a tangent line, shown in red, to the function y equals f of x at x equals a. So it turns out that we can use this tangent line, shown in red, as an approximation to y equals f of x when x is near a. So when we say x is near a, that means we have, terminology I've used often in this class, a is inside of a small neighborhood. I'm sorry, x right here. X is some element in this neighborhood of a, which is basically an open interval on the x-axis containing a. So if x is near a, okay, and I haven't defined what near is, then we can replace the definition of f of x by the equation of the tangent line at x equals a. And so that would be a huge savings in terms of computations of output values of the function. So, okay, so here we have the equation of the tangent line at x equals a right here. So where does this come from? Well, we know that the slope of the tangent line is f prime of a. Okay, so recall that this would be the slope of the tangent line okay, this would be the slope of the tangent at x equals a. All right, so there's your slope, and so now we have the coordinates of a point on the tangent line. So we have y minus f of a is equal to m times x minus a. So this is the equation of the tangent line to the function f at x equals a. And then, so we have y minus f of a. Now we know what the slope is. It's f prime of a, the derivative of the function at x equals a, times x minus a. All right, and then if we solve for y, then I'll write it down here. Y is equal to f of a, the function evaluated at a, okay, plus f prime of a times x minus a. Okay, so this is the equation of the tangent line, and if you are in a small neighborhood about a, in other words, if you're somewhere in this interval on the x-axis, this also happens to be an approximation for f of x on, say, a minus delta 1, a plus delta 2. Okay? And a is included in this interval. All right, so we have an approximation. And this is called the linear approximation because the tangent line is a linear structure, and oftentimes instead of writing y, we'll just say L of x. Okay, and this is read the linearization of f at a. All right, So it's nothing you need to really memorize here. It's just if you understand how to construct the equation of a tangent line to the function f at x equals a, then you can get its linearization. And this is valid for x values near a on either side of a. Okay. All right. So we can find the linearization of functions. So next page. So suppose I ask you to find the linearization of f at a. Okay, where f is equal to, where f of x is equal to the square root of x plus 3, and a is equal to 1. Okay, so the linearization, okay, from the previous slide, we want to solve for L of x. We want to find this function. So L of x is equal to the function, oh, sorry, that's a equals 1. And forgot to write my a. And a equals 1. Okay, so the linearization L of x is equal to f of 1 plus f prime of 1 times x minus 1. Okay, and so I guess we can calculate the derivative. So what is f prime of x? So f prime of x, so we use the power rule for differentiation, would be 1/2 times x plus 3 to the negative 1/2. Okay, so that's the derivative of f, and then we evaluate f, of course, at x equals 1. So we evaluate this at x equals 1. Okay, and so f prime of 1 is equal to 1/2 times 1 divided by the square root of 4, which is equal to 1/4. All right, so that's the slope basically. So the linearization then is equal to f of 1, which is 2, okay, plus the slope we just found, 1/4, times x minus 1. Which, if you simplify algebraically, is equal to 7/4 plus x over 4. Okay, so in other words, okay, here's negative 3, and here's the square root of 3. This is my xy plane. In other words, here's the graph of the square root of x plus 3. And so what this means is that we can replace this graph around x equals 1 with the equation of a straight line. Okay, so if x is near 1, this value of x right here, if that x is near 1 on either side, then we can approximate the square root of x plus 3 by this function. So for instance, suppose we want to calculate the square root of 3.98. Okay. Well, in this case, the square root of 3.98 is equal to the square root of 3 plus 0.98. So we'll take our x then to be 0.98. And that's pretty close to 1, right? I think you would have to agree that 0.98 is pretty close to 1 because you see how it has to match up with that right there, okay? Okay, so then we just take 0.98 and we'll plug it in here, and so we can say that 3.98 is approximately equal to 7/4 plus 0.98 over 4. Okay, so we have that. And that equals to 1.995. So this has enormous utility in, say, engineering applications where if you have a complex surface and you need to find, say, the value of at a particular point on the surface, you can replace short segments along a surface that has defined by a complex function with linear representations of that surface, and then calculate, say, some sort of phenomenal output at the surface using the equation of a straight line. This is a field called finite element analysis, and it's pretty big, and like I say, in a lot of engineering applications. So even though this example looks somewhat trivial and contrived, nevertheless, a lot of very complex math problems are solved using this technique. All right, so we can also say find an approximation for the square root of 4.05. Okay, and of course that is simply equal to 3 plus 1.05. And 1.05, of course, is pretty close to x equals 1 right there. So what we'll do, and the reason why I separated it out like this is because, remember, we're finding an approximation for x plus 3. So we have to calculate what x is. And x I've got here circled in red. So anyway, we know that the approximation of the square root of 4.05 is 7/4 plus x over 4, evaluated at x equals 1.05, like so. And then when you do the math, the answer will be 2.0125. All right, so that's the advantage of utility of linearization. Okay, so now remember on the previous slide, on one of these slides, was it the first one? Yeah. So go back to the first slide, and we see that this approximation is good on a certain interval. Okay. In other words, it has to be a very short interval, and so we would like to know for what values of x. I'll write this down. Okay. So for what values of x is this linear approximation accurate to within 0.5. Okay, so in other words, we want the truthful output minus the approximate output to be less than or equal to 0.5. Okay, so here's how we can express that statement mathematically. All right, so we know the truth is the square root of x plus 3. Okay, and we know the approximation is 7/4 plus x over 4, about x equals 1, in the neighborhood of x equals 1. So truth minus approximation, and then we take the absolute value of that difference, okay, and that has to be less than 0.5, okay. So this is somewhat of a brutal inequality to solve for, but we can of course use a graphing calculator derive the values for x. So we can do that. So let's try that. So I'll insert a browser, internet browser. Go to our calculator page. Okay, and so we'll graph y is equal to x plus 3, that raised to the 1/2 power, so that would be the square root of x plus 3 shown in red. And then the next graph will say, what is it, 7/4, y is equal to 7/4 plus x over 4. And this will be shown in blue, so there's your linear approximation. And then, okay, so we want to find the values of x, the domain on which this linear approximation is valid. So the range has to be restricted between negative 0.5 or 0.5. Okay, so we'll graph that. Oops, sorry. Y is equal to negative 0.5. Okay, so that's shown in green. And y is equal to 0.5. That's shown in purple. Okay, so let's look what we have here. So let me zoom. See if I can zoom in. So we'll zoom. Oh, that's zooming out, right? We want to zoom in. That's zooming out. Zooming in is this way. Okay. So zoom in very closely. Pan a little bit. So the red curve is truth. The blue curve is the approximation. And so we want to know we want our output to be within 0.5 of, let's see here. Okay, so we want to know, I need to zoom in some more, right? So how close can I zoom in? Oh, it's not. All right, so we know the truth at x equals 1 is 2. Okay, so the truth at x equals 1 is 2. So now, so we want our output to be within 0.5, right? So the difference between the two curves, let's see here. I guess what we'll need to do is we'll need to sketch the difference between the two. So another curve, I need another curve then. So let's plot the difference. So that would be x plus 3 to the 1/2 power minus 7/4 minus, oops, I need to set y equals that. All right, y is equal to that. Minus 7/4 minus x over 4. Okay, so that's shown in orange. Okay, so let's look at it perhaps from this vantage point. Let me get rid of this, get rid of this, get rid of this. Okay, so we want, can I zoom? Let's see, zoom out. Where's my curve? It didn't show up, did it? Oh, there it is. Okay. So we want, and then, all right, that's too much zooming. Okay, and then we want to find where this output is between negative 0.5. See if I can write it this way. Less than or equal to y, less than or equal to 0.5. Okay, so we have this band. And is that, okay, so I need to zoom in. So as long as this difference Okay. Well, okay. Not quite. Still not quite right. Let me think here. Let's try this. That's not useful information either. Let me give you something that would be more useful. Let's go ahead and say graph is the original function. So this is truth, okay? And let's say if we were to sketch the graph of y is equal to x plus 3 square root. Trying to think how we can best portray this. Plus 0.5. Okay, so that's the upper tolerance of our output, and then our lower tolerance would equal to x plus 3 to the 0.5 minus 0.5. Okay, and that would be our lower tolerance shown in blue. And then we can sketch our approximation, which is y is equal to 7/4 plus x over 4. Okay, and so that's shown in green. All right, so now let's see what we have here. So as long as the green curve stays within the boundary. You know something, I could probably do even better here. How about I do this? Let's make this interesting. So this is truth, orange is truth, green is approximation, and then the boundary, the envelope for which the green curve is a valid approximation would be something like this. Yeah, I'm just figuring out how to use this tool. So we would want the truth to be wedged between, let's see here, we would want perhaps something like this. Let's see, 3 plus x, see if I can try this, 0.5 minus 0.5, less than or equal to y, less than or equal to 3 plus x to the 0.5 plus 0.5. Okay, so yes. All right, so I think this is what we need. So let me interpret this graph for you. All right, so the green curve is the approximating curve, okay? The orange curve is the truth. The orange curve is the square root of x plus 3. And it's kind of hard to see in there because the band is purple. So what the purple band represents is it represents the range of, it represents a tolerance of plus or minus 0.5 on either side of the orange curve. So the purple curve, the band, I'll call it the band. So the band represents a tolerance. Okay. A tolerance of I misspelled that, didn't I? Represents a tolerance of plus or minus 0.5 on of the 0.5 of the output of the function. Okay, so 0.5 represents a tolerance of 0.5 of the truthful output of. So this is a range of the so 0 plus or minus 0.5 of the output of the square root of x plus 3. All right, so if we want our output of the square root of x plus 3, our estimate of the output to be, so what this means is, what the purple band means is, if we want our estimate of the output of x plus 3 to be within 0.5 of the truthful output, then we must fall, the output of our estimate must fall within the purple band, okay? And so notice here, at this particular point, right here, our estimate exits the purple band, okay? And so the x value of this exiting, where the green, or the linear approximation, which is green, where it exits, happens at negative 2.657, okay? So if we use a value of x less than negative 2.657, some x value outside of the band, then our approximation, our linear approximation, will not be within 0.5 of the truthful output, okay? And then here's the other point. So we can say negative 2.657 is the beginning of the interval. Negative 2.657 is the beginning. And if you can see that the linear approximation exits the band right here at x equals 8.657. So this interval represents the domain for the linear approximation for the suggested tolerance of 0, plus or minus 0.5. So as long as you can find your x value for your approximation to be on this interval along the x-axis, then we can guarantee that your output will be within plus or minus 0.5 of the square root of x plus 3. And this would be the linearization about the point x equals 1. About, well, not the point, but about x equals 1. So if you want to make this range a different interval, you want to make this domain a different interval for a different linear approximation, then you'll have to choose a different a value. This is valid for a equals 1. Okay, so if you choose another a, then this interval will change because the purple band, so the value of a will change. So if you say if you chose a equals 8, then your linear approximation may look something like this. Perhaps something like this, I'm guessing. Perhaps something like this, and you can see then the band will, the interval will change for its accuracy. Okay, so the interval, so this is good. So the linear approximation is good on this interval. All right. What can we do next? Okay, so how about we find the linearization of the natural log function at a equals 1. All right, so we'll do that one. So let me write that down. I don't think this is in the book, but we'll do it. We'll undertake it. So find the linearization for the natural log function at, what do I have, at a equals 1. Okay, and so the linearization, L of x, would equal to the function at 1 plus the derivative of the function at 1 times x minus 1. Okay, and so f prime of x, we know that the derivative of the natural log function is 1. And we evaluate that at x equals 1, and that's equal to 1. And we also know that the natural log function at 1 is 0. So our linearization then is equal to x minus 1. All right, so we can replace the equation for natural log of x with the equation x minus 1 as long as we're pretty close to x equals 1. Okay, so let's see here. All right, so I think that takes care of linearization. let's see here. Now we can talk about differentials. Let me see how I can deal with differentials. Okay, so I'm going to motivate the discussion with differentials by using an example. So differentials. And this isn't the part of the transmission of a car. This is a mathematical differential. Okay, so differentials. All right, so this would be question number 12 in section 3.10 of your text. All right, so suppose I give you a function like this. So we have y is equal to s over 1 plus 2s. And the question is, for number 12, is we want to find the differential of y. Find the differential for this function. So we want to compute. So when the question asks find the differential for the function, you just compute differential y. Okay. Well, we know that the differential of y over differential s is just the derivative of y. Okay, and so that would equal to the bottom function times the derivative with respect to s of the top minus the top function times the derivative with respect to s of the bottom divided by the bottom squared. So we just use the quotient rule for differentiation here, and so that would be what? 1 over 1 plus 2s quantity squared. And so the answer to the question then, the differential of y, which is the differential of the function, would just equal to ds, differential of s, divided by 1 plus 2s quantity squared. Now it seems kind of quirky this time at this stage of the game, but this will be very, very powerful when we get into chapters 5 and beyond of the text, because we'll need to deal with these a lot. So let's see here. What other question can I deal with? I'm looking at the book here. Let's see. Okay, so let's do, say, problem number 16. Is that the one I want to do? Yeah. Okay, so in problem 16, I'll do that on the next page. We're given this information. Okay, so we're given y is equal to cosine of pi x. Okay, and we're given x is equal to 1/3. And we're given that the differential of x is negative. This differential of x is equal to negative 0.02. And the question asks, find the differential dy. Okay, so we can find the differential dy. So dy, we have to use the chain rule here, is equal to minus sine pi x times pi times the differential of x. Okay. All right. And then it says, the next question asks, evaluate the differential of y for x and differential of x. Okay. So in this case, what we do is we have a value for x for the part B of this question, and then we have a value for the differential of x. And so quantitatively, we can compute the differential of y, which is equal to minus sine times the pi thirds, the sine of minus sine of pi thirds, radians, times pi, times a negative 0.02. So this would equal to what? The square root of 3 over 2 times 0.02 times pi, so whatever that is. You can use your calculator to simplify that if you want. Okay, all right. So 16, let me check if that's the right answer. Make sure I've got it right. Yeah, I think it's correct. Okay, so we'll go with that. All right, let's see. What else can we work on? So maybe question 20. So let's try question 20. Okay, so question 20 asks, we want to compute delta y and differential of y for the given values of differential x, okay? And then sketch a diagram, okay, showing the delta y and differential y, delta x and differential x. Okay, so, all right, so this would be number 20, yeah, question 20. All right, so we have, in this question, we have number 20. We have y. I tell you what, I have this worked out, so why don't I paste it in here and just discuss the solution. So I don't have to spend too much time writing. Okay. So let me, bear with me while I pull up the sketch for this solution. All right, so for this question, we're given the square root function, and we're analyzing the slope of the secant line. Are we? Is it the slope of the secant line? Yeah, the slope of the secant line and the slope of the tangent line in the neighborhood of x equals 1. And we're given that delta x is equal to 1. All right. So now, remember that delta y over delta x is the slope of the secant line. Okay? And that is equal to this formula, fx sub 2 minus fx1 over x2 minus x1. Okay, so recall that's the definition of the slope of the secant line. Now we're given that x is equal to, or x sub 1 is equal to 1. So we'll call x sub 1 is equal to 1. So we need an x sub 2. Well, x sub 2, okay, that would just equal to x sub 1 plus delta x. And since delta x is 1, x sub 2 is equal to 2. All right, so here's my x sub 2 right here. Okay, so now knowing that, we can calculate delta y. So yeah, we can calculate delta y. So delta y would equal to the square root of 2 minus 1 over 2 minus 1, which is just equal to the square root of 2 minus 1. Okay, and then we can calculate differential y. Okay, so we know that the derivative, the derivative, differential y over differential x, which is just the derivative of the function, that would equal to dy over dx, which is equal to 1/2 times x to the negative 1/2, right here. And then so the differential y would equal to 1/2 x to the negative 1/2, evaluated at x equals to 1 times the differential of x. And the differential of x, okay, we also know that, as we've shown in the past, differential of x is always equal to delta x, which is equal to 1. Okay, so differential y then must equal to 1/2. And delta y is equal to 0.414. Okay, and so the question asked to illustrate delta y, differential y, delta x, and differential x. Okay, so here is the illustration. So here's your delta x, right, in differential x. Well, here's the graph of the square root function shown in black. Since x is 1, I sketched and shown in red is the tangent line to the square root function of x equals 1. And then here's your q basically, and here's your p, right? And so delta y over delta x, delta y of course is the change in height of the secant line, which is shown in green. I'll show you. Here's your secant line. And then of course the differential would simply be, let's see, make sure this is correct. The differential would simply be this distance right here. It would be right there. Okay, so you basically extend a line parallel to the y-axis through point Q, and where it intersects the tangent line, okay, then you take the distance from this parallel line that is parallel to the x-axis and goes through P, so you take this distance right here, and that would be your differential y. So differential y is calculated based on plotting point Q on the function y equals the square root of x, and then extending that perpendicular up from this parallel line right here, and it's that distance. So you can see differential y is basically go to Q. An easier way of stating it is, so you go to point Q on the graph, okay, and then keep walking in this direction until you intersect the tangent line, and then draw this line parallel to the x-axis through this point of intersection with the tangent line, and that will annotate the differential y. Okay, so it's going to be like 0.86 units above point Q on the tangent line, right? So it's that distance. It's that excess distance. Okay. All right. So let me, perhaps I can, so try to understand how we can show what differential y as a distance looks like. It's this distance right here. Okay. It's the distance between these two lines right here. And the green upper line was found by taking point Q right here and drawing a perpendicular. So if we draw this perpendicular, like so. Okay. All right, so here, and point R is the intersection. Point R is on the tangent line, point Q is on the graph, and this is point P. Okay, so by construction, you can show what differential y is, and that's just from geometry. That's just a picture from geometry. Okay, so let's see what else is next. Let me see here. Normalization. I'm just scanning the problems that are in the text, seeing which ones are useful here. Okay, how about we try, say, problem number 36. Okay, this is a useful application of differentials. Problem number 36 in the text. So let me see. Let me see if that's the right one. Okay, yeah. So the question reads, use differentials to estimate what? The amount of paint needed to apply a coat of paint 0.05 centimeters thick to a hemispherical dome, with diameter 50 meters. Okay, so this could be, say, like a water tank or something. So in other words, you've got a hemispherical dome, diameter 50 meters, and you're going to apply a coat of paint that's, what, 0.05 centimeters thick, a very thin coat of paint. So how much paint would you need to cover the surface, to coat the surface? All right, so for a hemispherical dome, it's actually, we know that it's 1/2 the volume of a sphere, okay? And so for a hemispherical dome, we have the volume of the enclosure is equal to 2/3 pi r cubed. Okay, and so that means that the differential volume element, okay, that's going to equal to 2 pi r squared times the differential of r. Okay, so what this means is when we apply this thin coat of paint on the hemispherical dome, we're actually going to increase the effective volume of the hemispherical dome. In other words, the enclosure is going to be the boundary of the hemispherical dome is going to increase by 0.05 centimeters. And so effectively, we're going to have we're going to have an ever so slightly increase in the volume. So this incremental increase in the volume between the pre-coat and the post-coating, okay, this difference between the post-coating, the after-coating, and the before-coating, this is the volume. This is the volumetric difference between the volume of the enclosure. So it's going to be this, right? So now all we do is just plug in the numbers. So R is equal to what? 1/2 of the diameter. So that would be 2 times pi times 25 squared. And then the differential of R is 0.05 centimeters, which is, in meters, that would be 0.0005 meters, okay? And so when we calculate this, the amount of paint needed, when we multiply these 4 numbers out, we'll have 2 cubic meters, okay, which is a lot of paint. So you go figure out how many liters there are in 2 cubic meters, and then multiply the price per liter, and you can say this could be, what, several $1,000s worth of material just for that thin coating. Okay, so that's how we work those. Let's see. All right, so how about 37? This will be the last problem of this section that will work. I think that's all we need to do. So question number 37. Okay, so with this one, we have 2-part question. So it asks, use differentials to find a formula for the approximate volume of a thin cylindrical shell with height h and inner radius r and thickness delta r. Okay, so we want to find a formula for the volume of a thin cylindrical shell, all right? So the volume of a thin cylindrical shell. All right, so the volume of a thin, okay, so this is number 37. So the volume of a cylindrical shell, okay, is given by pi r squared times h. Okay, and so let me check. Okay, so we can assume that yeah, so that would be the volume of the enclosure of a thin cylindrical shell, pi r squared times h. Okay, now so a thin cylindrical shell, what that would mean is that it's like the paint coating effort. If you were to bump out the radius, so say a delta r, just a very tiny amount, increase the radius just a very tiny amount, increase or decrease it by a very tiny amount, you'll have an incremental change in the volume. And this would be the volume of the shell. So it would basically be, yeah, so it would be so this excess volume or this diminished volume. So let's just, for the sake of argument, say we're going to bump out the radius ever so slightly. So the change in the volume, okay, would then be the differential of the volume. So that would be 2 pi r h, and then we're changing the radius. Okay, so that would be your change, your incremental change in your volume. Okay, so this would be the approximation of the volume of a cylindrical shell. Okay, so it's a shell. So that means it's hollowed out in the interior of the shell. Okay, and this will be you'll use this a lot in Chapter 6. Now, what is the error between the true volume and this change in the volume? Okay, so in other words, we want to find. Okay, so we have delta V is approximately equal to differential of V. Okay, and so the error, okay, if we were to, all right, so the actual, what we've got here is the change in volume induced by increasing the radius versus the volume of the thin cylindrical shell. Okay, that would be like this. We would want, for the part B, we would want delta V minus differential V. Okay, and so that would be calculated like this. We would have pi times r plus delta r squared. Okay, so this would be the enclosure. It would be delta r minus the actual enclosure. Okay, so this would be the change in the volume of the cylindrical shell if we were to increase r ever so slightly, minus the volume, of course, of the cylindrical shell. So that would be 2 pi RH delta R. Since differential R and delta R are assumed to be the same. And so this would equal to, so what we'll get then is we'll have pi R squared H plus 2 pi RH delta R plus pi let's see here, delta R times delta R squared H minus pi R squared H minus 2 pi RH delta R. Okay, and so this is equal to pi times delta R squared H. Okay, so delta volume minus differential volume would be that. And so this would be the error. This is how you calculate the error. Involved. So all right, so that means this would be very similar to example 4 in the text on page 254. Instead of using a cylinder, they used a sphere. And so the error, so what differential R means is it's the error in measuring the volume of the cylinder, okay, measuring the radius of the volume of the cylinder. And so this this quantity that we just calculated would be the basically the error in the volume, okay? When the error in the actual volume when you have an error in the measurement of the radius. Okay. So let me see here if there's anything else. Okay, we've got relative error. Relative error, okay, would just be is equal, so delta V over V is your relative error. And note that delta R is equal to differential R. Okay, so just a couple of other things. Let's see, is there anything else? Okay. All right, so I think we've got that covered. Okay, so that's all I want to say now for section 3.10. Differentials, applications of differentials, and linear approximations of functions. So why don't we go ahead and go on to the last section of this chapter, section 3.11, where we talk about hyperbolic functions. Okay, another class of functions. So a lot of definitions in section 3.11 to close out. All right, so I'll end this lecture and I'll start another video for section 3.11.